Well, it's official, folks. We can get started. Welcome back, everyone. I just want to start by saying I remember being a student pretty clearly about 20 years ago that this class was always really hard to make it to. I usually skipped it since it's hard to come right before a holiday. But I really appreciate everyone making it in. We still have pretty important work to do. These are the last two sections of the entire semester, and they happen to be the trickiest. Sorry about that. Statistics is just kind of stacked that way. You have to get through all that material just to say, how does a hypothesis test even go? It'd be nice to do this in the middle of the semester when we had a little bit more energy. But whether you're showing up today in person or virtually, thanks for making it in. It's not easy to do that right before a holiday. So this is our final quiz, quiz number 10 due today. But if you don't have it quite finalized, I do take all quizzes late. So over the long holiday, it could be a great opportunity to get caught up as well. So we're going to be working through section 15.3. Looks like we have just two more examples to go through on hypothesis testing. And then in section 15.4, we do it all over again. Hypothesis testing now for quantitative data. We're looking into population means this time. But it's not as bad as it seems because once you get through hypothesis testing once, you'll notice that in 15.4, almost exactly the same. You just have different slight alterations on the test statistic and what you get your p-value from. But all that stuff about left tail test, a two-tail test, a right tail test, all of it is literally exactly the same. The logic of when you reject or fail to reject, all that carries over directly to this section. So usually this one goes a little bit faster because we just don't have to explain as much stuff, but we'll still go through it very, very carefully like the other sections. Well, any other questions or comments folks would like to discuss before we get started? Okay, well, let's give these last two sections a try. We're definitely not going to get too far into 15.4. And if it makes sense to end a little bit early since of a lack of time or something like that, we might just hold off on this till after the break, since doing a little bit of 15.4 and taking a whole week off means we just practically have to go over it all over again anyways. So let's take a look then where we left off in 15.3. We set up a hypothesis test. Looks like we did the parameter, the null alternative, and just copied down the level of significance. So just as a quick rundown of what we were looking at, this has to deal with distracted driving. They gathered a a representative sample of 283 Americans in this age range. We're told 74 indicated they had sent a text message while driving. So this is self-incriminating, basically. You always have to think about that in the data. It doesn't mean exactly 74 text while drive. These are the ones that were just willing to indicate that they did. So the question was, does the data indicate that more than a quarter of these Americans in that age range have sent a text message while driving? This was really very tricky right here. When it said a quarter, that was the value to be tested in the null hypothesis. So we set up the parameter. P is the population proportion of all 16 to 17-year-olds that text while driving. The null hypothesis is a statement that it's exactly a quarter, not more than, not less than, nothing's changed from this expectation. But the alternative hypothesis, we're now testing that it is more than, so a right tail test, 0.25 for the quarter. So we copied this down just as a quick reminder so we didn't have to look it up at the very top of the problem. A p-value has to be below 0.01. It can't even be exactly 0.01. It has to be literally less than that in order for us to accept that alternative hypothesis here. First thing we want to check out, though, are the conditions. Let's go through kind of the busy work on this one quickly. Well, we don't have a random sample, but we're told the sample is representative of Americans in that age range. So we'll go with that right there. The sample is at least representative of all Americans in this age range. And that's a very shady thing to say out of nowhere. It is accepted in our conditions. Our conditions wants a random sample or at least a representative sample. Sometimes this happens usually more likely in medical settings where people are dealing with someone with a rare condition. They can't necessarily get a simple random sample, so they use a convenience sample, the people who are just readily available, maybe the people in their practice, to form out their sample. They then have to argue that this sample really does represent all of Americans, that there's no biases there. And sometimes that work, explaining why your sample really is representative, well, not random, is more work than the actual study doing the hypothesis test by far. The explanation of that could be pages and pages. It's pretty awful. So we'll trust them and go on to the next step, where we're just checking if our sample size is going to come out large enough. So this is the one we probably want to be really careful on. On this, we'll take a look into expected successes when H naught is true. Let's go with a two-column system this time, just for saving on vertical space. This is the expected failures when H naught is true. When we're saying H naught is true, we are saying that the value P is truly 0.25. So if we go to grab our sample, almost wanted to say random sample, but if we have a sample of 283 people representing that age range, then we expect 25% of that sample to be successes. So we'd be taking n times P naught, which is in this problem, 283, multiplied by 0.25. So 1/4 of 283. Let's just go with a times 0.25. That gives us 70.75 successes. It had to be greater than or equal to 10, so we meet that benchmark there. I'll put a small check on a lot of these problems just to convey that was what we wanted to see, greater than or equal to 10. That means we're probably okay on the expected failures. There's more failures on this one. It's going to be, let's go with this formula, n minus 70.75. This is probably the more sensible way to do this kind of calculation without getting mixed up in a whole separate formula. It's the observation that the expected successes plus the expected failures have to total back to the whole sample size. Once you get this, you might as well just go 283, hit minus, you can even go up arrow to just paste that down, 70.75. So we get 212.25 failures. This is also greater than or equal to 10. So now from condition 2, we're able to say the sample size is large enough and conditions are met. We hope. There's a lot of trust that goes on this particular problem. We know the sample this time is not random. They straight out told us it's just representative. So it's always good to be really skeptical whenever you read a study that says that. This right here is a shady assumption. And it really does take a lot of evidence to really explain why it simply is representative when you didn't gather things by random. So we're not trying to really tear apart the study. That's not really our place in an intro stats class. But it's good to know when things just seem a little bit weird in statistics. This is one of those times. Any questions at all, folks, with the conditions at the moment? Okay, now this is the fun part. Calculate the test statistic always goes about like this. Let's write this out in a sequence of steps because it is kind of a big step. For the test statistic, first thing you definitely want to do is write down the formula. Really good advice there because now you know where everything's going to plug in. You'll have z equals p hat minus p naught. That came from the alternative hypothesis, or excuse me, well, the alternative over the null hypothesis. We usually think of the null, though, when we think of P naught, divide the whole thing by standard deviation of p hat. So that's our formula. Step 2 would just be to calculate some of these elements in the formula. So in step 2, compute first it'll be p hat. Next it'll be standard deviation of p hat. And we already have the value p naught, so we'll just look it up and drop it in. So let's see if we really do have to do a computation. Let's see here. Yeah, it looks like we do. All we know is that there's 74 successes, sample size of 283. So we go 74 divided by 283. So this is going to be the percentage of the sample that of these people in that age range that texted while driving. It is 74 divided by 283, and it comes out to 26.145%. So 0.2615. Sorry, said that in a weird way. 0.2615 after rounding. I said 145. That doesn't quite make sense. So we get this value out. And now this is where statistics becomes kind of fun in a certain sense. Now that we've done a lot of work on statistics, inferential statistics, you now know that if this is at 0.25 and p hat is at 0.2615, that is in no way evidence that the alternative hypothesis is true. Seems weird, right? The alternative hypothesis is saying p is bigger than 0.25. P is the unknown parameter, but it's approximately equal to p hat. So why isn't this true? Well, it's because we're looking for a high level of evidence. We want to say that the probability of collecting the data as extreme as this, or even more extreme, under the assumption that the null hypothesis is true, is less than the probability of 0.01. If we can really say that, then and only then can we support the alternative hypothesis. So just because your statistic looks like it's significant doesn't give us the right information whatsoever. This will get us closer because it's going to measure how many standard deviations the statistic is away from the hypothesized value. So to get that, we have to actually calculate the standard deviation. So that's this step right here. Probably going to need more vertical space. It's going to go square root. Let's put in the formula first and match up the color coding. This is really very tricky because if you go by muscle memory, you're probably going to be tempted to put p hat here. I know I am. But in hypothesis testing, if it's the standard deviation, we're putting p naught inside instead. Then 1 minus p naught, division by n. So just like z, it's a good idea to write down the formula. Same for the standard deviation right here. It helps with accuracy and just learning the formula as well. If over the course of studying for the final exam, you just write that down, maybe 10 times studying, you're probably going to memorize it just by brute force at that point. So standard deviation, p hat, using our numbers becomes, follow the structure and grab p naught, which came from right up here, that 0.25. Let me get rid of that temporary highlighting. Then it's 1 minus 0.25, or 0.75 if you want to skip a step. Division by sample size, and I constantly forget that, but it's right here by p hat. You're always dividing by the sample size, so it's 283. So we'll round this one to 4 decimal places, and in the calculator, carefully hit second key, power 2 key, 0.25 times 1 minus 0.25, or if you prefer, this is not a bad one, to go just at 0.75, then divide by 283. Our value should come out as this right here. How's it looking so far to folks? Are we all getting about that figure? Okay, so let's record our official result. Standard deviation of our statistic is 0.0257. 0.0257. Okay, now that we have that down, we can go back over here, and this is what I would consider a good step 3. Evaluate Z. So evaluate Z, what I mean by that is just plug in the information that we've found so far. Z is now equal to P hat first at 0.2615. Subtract from that P naught, which is at 0.25. And then finally divide everything by 0.0257. So now we're going to figure out, is this really evidence against the null that we really have more than 25% of teenagers in that age range texting while driving? Well, let's calculate 0.2615, subtract the 0.25, divide by our standard deviation, 0.0257, and here's the number of standard deviations. It came out to 0.4475. And you know what? That's not a lot of standard deviations at all. That's typical. And if it was a 1.44, that's not a lot of standard deviations either. Usually things become more significant, more extreme, right around 2 standard deviations or more. So this one is 0.4475. Not a whole lot of standard deviations. That means our data is actually consistent with the statement of the null hypothesis. This isn't too unusual. P hat isn't very far away from the hypothesized value in terms of standard deviations. This is almost an assurance that we're going to fail to reject the null hypothesis. We still have to give a p-value. People want to know how badly you missed the target, so that's going to be our next step. Any questions at all, folks, with part C? Okay, statistics always kind of goes like this, by the way, where some of the parts are really hard context dissections like this, setting up parameters and hypotheses, checking conditions. But then the rest of it is just running with the numbers. Sometimes people hate this part and love this part. The other people's go the other way. So it all just depends on, I guess, your personality, style of learning. But at the end of the day, we can all do both parts. It just takes practice to get there. So as far as the p-value goes, we need to look up our hypotheses. The major thing we need to know about them is, what kind of a test was it? We might as well take a bigger screenshot since we'll eventually need all of this stuff for our conclusion. Okay, so for the p-value step, we look right to here, to the alternative hypothesis specifically, and determine the type of test. If there's a greater than sign, as we see it right there, that tells us this is a right-tailed test. At this point, if you're doing a quiz problem or a problem in my stat lab, you can go up on the notes here, and it describes p-values for any kind of the 3 tests. But let's just write it down here. It's a little bit faster. Right-tailed test will have this picture. N01 means normal distribution, centered at 0, standard deviation 1. Next thing we grab is Z. It's at 0.4475 standard deviations. So you know what? It's this time pretty close to 0. It'd be about here. Next, because we said it's a right-tailed test, we want the area going off in this direction, towards the right. It's kind of nice that there's some internal consistency there. Always look towards the alternative hypothesis specifically. It's telling you the direction to shade. Greater than sign means shade going that way to the right. You can almost imagine that as like an arrowhead as well. So now with this setup, we can say this is input 1, the lower bound. Input 2 is 10 power 99. And same inputs for the last 2, 3 and 4 are 0 and 1. We use normal CDF. And this is enough information to state the p-value in now one go. We don't have to double anything. It's not a 2-tailed test like on the prior example. We just want that area there. So go second, bars to pull up distributions, go down to option 2, normal CDF. And lower should be 0.4475. Upper is already set correctly, 10 power 99. And really so is the rest of this stuff. This was carrying over from our two-tail test that we did just last night. Kind of neat how the calculator remembers all this stuff. So hit enter a couple times, and that's our p-value. So if we want to support the alternative hypothesis, we want small probabilities because we want to say it's extremely unlikely to get p hat at 0.2615. But that's a high probability. So this time, we're going to fail to reject the null hypothesis because that as a p-value is not below 0.01. So let's write that in. 0.3272 upon rounding. We can make one extra statement if you'd like. That goes, this is bigger than 0.01, which is equal to alpha. Actually, let me change my color on that just to kind of tie these together. That 0.3273 is bigger than 0.01, which is equal to alpha. And this tells us we will fail to reject H naught. Well, we are just about there, folks. Any questions so far before we go to our practical conclusion? Okay, so this is where it gets really tricky. We know if the p-value was smaller than 0.01, we would just write out a statement that went, we have significant statistical evidence that p greater than 0.25, saying what p is in the context. But now that we failed to reject the null hypothesis, there's the surprising part. We still don't accept the null hypothesis. We just write a statement that says, failed to support this. Earlier in the notes, we said there's only two conclusions in hypothesis testing. You'll either conclude you have evidence this is true, or that you lack the evidence that this is true. And 16 to 17-year-old drivers might think that this is great, that we found evidence that they are not above 0.25 in their percent or proportion of texting while driving, but that's not true either. This doesn't support that they're below or at that at all. All what that happened is we lacked evidence for that statement being true. So we go on to say next, this study does not provide significant statistical evidence to support the claim that we have to read out the parameter P, all 16 to 17-year-olds that text while driving. Let's say here, let's go to this part, is above 25%. So that would be our claim right here, or our conclusion right here. We just didn't find that support in this problem. Well, any questions at all, folks, with our conclusion there? Okay, well, this is where the analysis would end for this one. Again, people would sometimes request a confidence interval after this one, but that would be a tricky confidence interval to give with this kind of analysis, because if it's a right-tailed test, it is possible to have your conclusions from that hypothesis test be different than if you were to give a confidence interval analysis. That's really pretty weird, but the more you get into statistics, the more you realize our confidence intervals that go like this have a lower bound and upper bound can also be changed. If you're doing a right tail test, you can give a confidence interval that has one number and then goes off to infinity to match it up. That confidence interval would agree with the hypothesis test. But our book doesn't get into those weird side topics. So the thing to take away from this is, if you're doing a right tail test or a left tail test, your ordinary confidence interval cannot be used as a follow-up analysis at all. You could even have contradictory conclusions going that way. Let's actually add that to the notes just as a parting statement to this one. Since this is a right-tailed test, a follow-up procedure is a confidence interval of the form A to infinity, which again, our book doesn't cover it, but the major reason that we're saying it here is we can't give the original confidence interval that we know and love that has two finite numbers. It would have to be something like this, really kind of weird. But we did it in either case, folks. That's the conclusion of this problem. Big takeaway with this example is we need to see what happens in an analysis when we fail to reject the null hypothesis, what the conclusion looks like. Because in my opinion, this is one of the trickiest conclusions ever. Any questions at all, folks, getting through this one? Okay, well, we've got one more example to get through then. This one was a right tail test. So if there's justice in the world, the last one should be a left tail test. So let's hope for that. No guarantees, though. I think I forgot how this one went. Starting off, it says, the report, A Crisis in Civic Education. This is from the American Council of Trustees, Alumni, January. They seem like a pretty interesting organization. They summarize data from a survey of a representative sample, there's that word again, of 1,000 adult Americans regarding their understanding of US government. My school was Bonneville High School, and my government teacher was a PE teacher, so I'm probably not as well educated as I should be myself, if I'm totally honest. But it goes on to say, of the 459 of the adults in the sample, excuse me, let me try again, only 459 adults in the sample, of the 1,000 in the sample, were able to give a correct response to a question asking them to choose the correct definition of the Bill of Rights from a list of 5 possible answers. So that's a pretty big statement right there. And this last part, when they said correct definition from a list of 5 possible answers, that's even more serious in a certain sense, because it's telling us they made this question easy. It's hard to define the Bill of Rights just by saying it, but if you're presented with a list of choices, it's way, way easier. But still, only 459 of the 1,000 could get it right. So that's actually a pretty tricky question for the average American if the sample truly is representative of all Americans. So the question right here goes, let's actually separate this out. Determine if there's convincing evidence that less than half of adult Americans could identify the correct definition of the Bill of Rights at 5% significance level. So that's our whole statement so far. Let's start writing down information that we can definitely identify. It says sample of 1,000 adult Americans, so that would be our sample size. N is 1,000. And looks like when they said 459 did something, exactly, that's the successes in the problem. So 459 successes, that's correctly identifying the Bill of Rights in a multiple choice question. So 459 successes. Now, this one's not really a question, it's more of a demand, but it's still the statement of the alternative hypothesis. Usually if that's written as a question, it's a dead giveaway. They're talking about the alternative hypothesis here. But you could totally turn this into a question if we needed to. We would just say, is there? rather than saying determine if. Convincing evidence that less than half, if your eyes paused right here and you thought to yourself, left tail test, good on you. That's the keyword that's indicating it right at that spot. The less than, really. So this less than right here tells us we have a left tailed test. Then it says half of adult Americans. That word half there is kind of rude. It's like the quarter in the last problem. Exactly. We have to take that, translate it into actual mathematical statement we could put in a calculator. It's a statement of the hypothesized value, P naught, is 0.50. So half of adult Americans could identify a correct definition of the Bill of Rights. This part right here is also important. Use a 5% significance level. This is telling us alpha equals 0.05. So we're trying to find a p-value below that in order to accept the alternative hypothesis. And I think that's pretty much the whole context so far. At this stage, you're ready for the hard steps, coming up with P. So this is definitely categorical data. There's no units on any of these numbers, just successes versus failures. So we can say P is the true, I'll go with percentage on this one. And I've been trying to vary these statements a bit as we go, just to kind of convey, you don't have to say it exactly one way. You have to indicate you're talking about a population, proportion, or percentage somewhere in the problem. So it'll be the true percentage of all. We need to pause here and think, what is the sample on this one?
All Americans regarding understanding the government.
Yeah, absolutely. So the population would be the all Americans, and the understanding of the government would be the successes there. So we'll say P is the true percentage of all adult Americans. So let's do this in the same way we kind of did before. Let's indicate that this is the population. Let me get some extra white space here. So this part is the population. And we can write out exactly what they said here, able to give a correct response to a question, asking them to choose a correct definition of the Bill of Rights from a list of 5 possible answers. There's no harm in doing that, but if you paraphrase in a way that still captures that information, that's always just fine. Let's paraphrase on this one and say, true percentage of all adult Americans that know the definition of the Bill of Rights. This is not the complete context because we set the bar extremely low on how well they know the definition by making it multiple choice. But again, that's just still tying into the original context. We're still going to be thinking of this as we go through the problem. We don't necessarily have to write everything verbatim all of the time. But this part right here, knowing the definition of the Bill of Rights, is the successes. So for categorical data, as far as the parameter goes, this is pretty much the approach each and every time. If you go back to the notes, you'll notice we did it that way for confidence intervals, as well as for hypothesis tests. Next thing we check is if the conditions are met. Let's see here. We have 459. Our value to be tested is 0.5, but I think I'm jumping the gun, aren't I? Sorry, we got the parameter down. I must have been thinking confidence intervals where you're just done right there. There's more to this story. I should probably put that in yellow this time. We still need the null and alternative hypothesis. So sorry for almost, it looked like we were out of space, like we were done, but let's keep on going on this one. We need a null. Let's say it this way as an actual sentence. Test H naught, so a statement will go there, against HA, another colon, another statement, using alpha at 0.05. So sometimes when people write hypotheses, they just make it a big overall sentence altogether. I guess a sentence does need a period. So if you like writing it out that way, that's a great way to format your answer. We'll take here the parameter we defined in both hypotheses. Next, we take the hypothesized value, half of Americans knowing this definition. They'll go here and here. Hypothesis testing is truly tricky though, so let's leave this last bit to the class. Starting with the null hypothesis, anyone see what would go right here by the red dot?
The left arrow, right?
Not in the null hypothesis though, something else would go right there by that red dot. It'd be equals, absolutely. So equal sign would go here. And just for the notes, equality always here. Sometimes that's an easy thing to forget when you're running through these problems and get mixed up what should go on this location here. And if you learn statistics out of a different textbook, that might seem a little bit weird. The author that we're learning the book out of will always put equality in that location. Some textbooks differ a little bit with either a greater than or equals or a less than or equals. But the next part, because it's a left-tailed test, what should go on this portion? Exactly, so we'll go here. I think you indicated basically put that down. Yeah, so we put that value in, and that's our full statement of our hypotheses. So we're testing this null against this alternative. Sometimes people say versus, using that rigor of evidence, 0.05 significance. Well, any questions so far, folks, with our hypotheses? Okay, for condition checking, let's do another screenshot. About right here should get us what we need. As far as determining the conditions are met, we'll go pretty much the same way as last time. We check if we have any information on randomization. There is none. That's always a concern. We're told the survey had a representative sample. So it looks like they probably just grabbed people who signed up, maybe to a workshop, something like that. Maybe they looked at the demographics of these 1,000 people and argued the demographics of these 1,000 closely match the demographics of the entire United States. If that's accurate, we might be able to trust them, but you should always feel a little bit uncomfortable about that because a lot could really go wrong. It's easy to think your sample is representative and then something happens, you realize it really wasn't, your sample was flawed. Think of like, for example, elections going awry, even though polling indicated one direction, oftentimes polling is just wrong. It's the sample that was the problem many times. So here we'll say what we saw, the sample is representative according to the study. So if it being a representative sample makes you as uncomfortable as it makes me, sometimes you can shift blame in this clever way by saying, according to those guys, they said it, not me. So that's something you could always pen into there. For step 2, it's something that's a little bit more specific. We're just checking the expected successes, expected failures. So let's run through that portion. So right here, I'll just this time call it very briefly expected successes. On the right column, expected failures. Formula will go for the successes n times P naught. The sample size n was 1,000, and P naught is at 0.5. I think that's going to be our easiest sample size check ever because now we're just cutting it in half. We have 500, which is definitely greater than or equal to 10. So we meet that benchmark. If we have 500 over here, then expected failures is exactly 500 as well. let's write it down just for the sake of the notes. N minus the successes we found, which is going to come out as 500. Actually, let me add just a little bit more detail. Let's substitute in the value for N. 1,000 minus 500, which is now equal to 500 again, greater than or equal to 10. So we can say the sample size is large enough and the conditions are met. Well, we've got through the tedious part of hypothesis testing, saying what the parameters are, all the hypotheses, checking conditions to see if we can even use the test. You'll notice that the conditions are pretty much always being met. The only place where it gets a little shady is here, or if we just don't even know if it was random or not. But we're not going to have statistical problems where conditions are not met, and then you're being told, do the procedure anyway. That would be really, really weird. So that's why in this class, we check it to see when it is met, but you can almost guarantee that these problems, they will always be met. So now we're off to the test statistic and p-value, and then we'll make our conclusions on this test here. Any questions so far, folks, to this stage? Okay, let's copy the same format as we did before. Step one, just write down the formula. The test statistic is Z for categorical data, and its value is going to be p hat minus p naught divided by standard deviation of p hat. So same exact approach as before. Then we go over to the margin and start calculating some of these elements, which is a pretty good thought in a certain sense, because there really is a lot of stuff happening right inside here. So the idea with step two is if there's a lot going on in your formula, then just divide it up and conquer. So we're just going to look at one element at a time. We're looking at the trees, not the forest, essentially. So we'll leave this mess alone and just calculate p hat. That means we need to go back up here. I shouldn't have deleted that. Let me grab it again. Okay, so to get p hat, we take the number of successes, 459, divide by the sample size, 1,000. I kind of like this problem. This is so far, it hasn't really needed a calculator. If you're dividing by 1,000, you're just putting your decimal place 3 spots to the left, 0.459. We're going to definitely need the calculator on the next computation. But now that we have the statistic, the next thing we want to calculate right after is standard deviation p hat. I mean, you could do these out of order, but this is a decent way to do these, I'd say. Would be the order you do them in confidence intervals. The reason you could do them out of order is because standard deviation p hat didn't depend on p hat. It depends on p naught, its value. And we said p naught down here in the context is 0.50. So it's going to be 0.50 times 1 minus 0.50, which is just 0.50 squared, divided by the sample size again, which is at 1,000. So there's often a lot of consistency with these two formulas. You'll know you're on the right track. It looks right on paper if this denominator matches up with that denominator. And the values going inside here. Yeah, so the values here would be different. Yeah, just the denominator would be the same. Well, any questions, folks, before we jam that into the calculator? Okay, let's work this out. Hit second power 2 button. We're going to go 0.5. I'll just write this as 0.5 times 0.5, since that's what we'll get in this group right here. Divide by 1,000. And our standard error in this problem, standard deviation in this problem is exactly 0.0158. Well, any questions, folks, with that value? Okay, so last thing to do now, after computing all that, step 3 is just the synthesis. We're bringing everything together. We go to step 1, write out Z once more. And I think we mentioned the method here sometimes is called lovingly by math people, plug and chug, where you see P hat, plug in 0.459, subtract value for P naught. It's written down right here, but you'd usually be looking to what you said in this spot or the null hypothesis, 0.50. And then the whole thing is being divided by 0.0158. So we're just about there, folks. Putting this into the calculator, it doesn't look like there's a big difference between the two until you consider standard deviation is kind of small in this problem, as it should be because the sample size is pretty large. So let's see how big Z really is. 0.459 minus 0.5, then division by 0.0158. That gets us negative 2.5949. And you know what? That's quite a few standard deviations. We still need to calculate the p-value every time we get the test statistic, but this sort of sets up your expectations. If this is going to be a left-tailed test and we're almost 2.6 standard deviations, we're probably going to have significance on this one. Unless alpha was set to like a 0.01, something really, really low, then it's still kind of up in the air. Well, we're done with that part. All we now need to do is come up with a p-value. To get our p-value, we have to recall what kind of a test was this. I think it was a left-tailed test. Let's grab this in case we need it. We probably will pretty soon. We want the parameter p as well as the hypotheses and even the level of significance. Think of the screenshot that we write down as basically this is where you're looking on your paper, where you probably have a bigger view than what I have here with all the scrolling. Okay, so I think this should get us ready to go. So with that test statistic Z, the first thought you'd want to have is recall from your alternative hypothesis, the less than direction tells us left tailed test. Knowing that gives us really quite a lot of power here because now we can say the computation is going to look like this pictorially. So same statement, this is the normal distribution with a mean of 0, standard deviation of 1. Our test statistic is way to the left this time. Somewhere about here visually is where I would think it is. So Z is negative 2.5949. When we said it's a left-tail test, we put on a vertical line segment right where Z is, and now shade to the left. Even though this diagram right here isn't strictly required, it really is a huge help because now you know exactly what's going in the calculator and in what order. So this time input 1 is the lower value at negative 10 power 99. That's because we're shading to the left forever, not stopping. The upper value is the test statistic this time. Let me write out this way. That's input 2, upper. Then input 3 and input 4, like before. Usually it's not a bad idea to just skip that because we know those are always going to be the last two. So from that diagram, we now have a p-value we can report. We just have to print it out from the calculator. So once again, second bars. I think we've said second bars like 100 times so far this semester. Go down to normal CDF. So our lower value is the largest negative number supported. Hit the negative sign down here to the left of enter, kind of kitty cornering down and left. 10 power 99 because of the shading to the left. And then for the upper value, negative 2.5949. So negative 2.5949. Double checking those. I have a bad habit of miscopying this stuff. Then 0.1, and we should be all set. So that's what your calculator should look like right before getting the p-value. Enter a couple times, and there it is, 0.0047. This is a very small p-value, so it looks like our data is even more significant than I was thinking initially. This is well below any alpha that we would typically put down, even 0.01. So we have 0.0047. Let's write down this next thought. That value we just found is less than alpha. Let me write it this way, less than 0.05, which is equal to alpha. And so this time we will reject H naught in favor of HA. This problem in part D, it just wanted the p-value. So let me put this in a box just to convey. That's all you really need to say. But it's good to write this down as well because it's kind of organizing what you're going to do very next when you get into the conclusion step. So that's what we're going to do very next, give the practical conclusion. So we did it, folks. After the test statistic, the p-value is the next trickiest step. Any questions at all in obtaining that one? Okay, and I think it's a good point to say now that this is the major reason we looked into the normal distribution in chapter 5 in the very first place. It wasn't because the chapter 5 problems using the normal distribution were like the most amazing problems ever. It was because hypothesis testing is the important thing that we want to do all along. So we just needed the normal distribution for that. So now, down below, here's what we get to say. We're rejecting the null hypothesis, so there it is, it's gone. We have evidence that that's true. And so we go on to say, this study provides significant statistical evidence that, I'll keep with the percentage like we called the parameter, the percentage of all adult Americans that know the definition of the Bill of Rights my hand is actually getting tired at this point, that know the definition of the Bill of Rights is less than, let me use that same color, 50%. Here we took the hypothesized value and just converted it to a percentage because we said percentage at this step. So that's not the most wonderful view of adult Americans, but at least it's honest. This is probably really likely to be quite true if they retest it at any given year. Something has to change with the American education system, I think, to make this go the other way. And those changes sometimes take a long time to actually see in the data. But we did it, folks. Aside from the kind of depressing outcome of the statement right here, that's what a full hypothesis test would look like when we have actual statistical significance. So always remember, you're looking for small p-values, smaller than whatever alpha is. The problems will often say what it is, but there's a chance that you might have to come up with your own. So it would either be a 0.01, a 0.05, or a 0.10. Well, we did it, folks. That's the conclusion of hypothesis testing if we're dealing with categorical data. What we'll be doing next is switching over to now quantitative data. But any questions at all, folks, with this conclusion here? Okay, let me get this saved up. It's trying. I forget how long this document gets. Digital ink is a little bit rough on Microsoft Word, so it made it good news. Our next section that we're going to be getting into, our final section of the entire semester, will be this one right here. We're getting right back into the central limit theorem. And the central limit theorem statements are what we needed to get a confidence interval going, but it also works to help us with the hypothesis test. In these notes, we'll review what the standard error is from chapter 14 and degrees of freedom. Then we're just going to jump right into the test because so much of the information does carry over. You will calculate a test statistic, and notice how similar that is already. Kind of similar. There is some differences there. On this page, where it says calculate this test statistic, that's what we were doing right here with the test statistic. Here's the changes though. We put in the sample mean, so that's why there's a Y bar right there. Let me get this thing out of the way. Uh-oh. There we go. So we have a Y bar instead of P hat. That just means we're changing the statistic because we have quantitative data. We have mu naught, the hypothesized value, instead of P naught. But here's one big change. Knowing the standard deviation happens really well for proportions, but not for means and with quantitative data. We still have to use the standard error in this part. But you know what? In a certain way, that makes it a little bit easier. It means when you're doing things with a confidence interval or a hypothesis test, you're not making a big change like this. It's standard error each and every time. It turns out the alternative hypotheses and the p-values go exactly the same, but we'll still describe them when we come back. And then, so do the decisions. And these are going to be the first problems that we'll take a look at when we come back from the long break on Monday. And we have a couple examples here. So we'll also decide on Wednesday when we come back. That'll be Wednesday the 4th, if we want some more examples after these two here. But like we mentioned before, we could make some headway into these notes, but after a long break, we would probably just need to redo everything there. So we'll end class a little bit earlier today by about 12 minutes and some change. If you have any questions, I'll be here because I have a 7 o'clock class. I can't go anywhere. I'll be happy to help out. Otherwise, have a wonderful Thanksgiving break, everyone. Stay safe. If you're getting caught up in working, I'm checking my email every morning of the break, so I'll always get back to you. Otherwise, I'll see you all back on December 2nd. Have a great one.
Thanks.
Thanks.